Okay, so we'll now look at the problem of maximal matching of edges. So what we'll do is we'll first look at some terminologies and then go through some algorithms in detail. Okay. Alright, so what is a matching? So given a graph with vertices and edges, matching is a set of edges such that no two edges in the set have a common end vertex. So for example, this is a matching that has two edges in it and there is no common end vertex for these two edges. Similarly, this is a matching of three edges for this graph and there is no common end vertex for any two edges in this set. So all of these are matchings for the graph here. And if you pick any of the sets for any two edges in this set, there's no common end vertex. So 1, 2, 3, 4, 5, 6, 7, 8, 1, 5, 2, 6, 3, 7, 4, 8. So in any of these sets, you cannot find for any two edges a common end vertex. So all of this can be called as a matching. Now, what is a maximal matching? So a maximal matching is a set of edges such that if I add any more edge to that set, it will violate the property of matching. So for example, this is a maximal matching because if I add any more edge to this set, so from this graph, so if I add the edge sets, edge say 5, 6, 5 is already there. If I add say 3, 6, 3 is already there. So I cannot add any more edge to this set to maintain and still satisfy the property of matching. So such a set of edges is called a maximal matching. That means we cannot add any more edge to this set without violating the property of matching. Now there could be more than one maximal matching of edges for a given graph, so something like this. So here you have 4 maximal matchings. And you notice here 2 of them have just 3 edges in them, whereas 2 of them have 4 edges in it. Okay, so it depends on which combinations of edges we pick. If we pick some edges to be part of a matching, we cannot add a lot of other edges to this matching. So that's part of the criteria that we'll use later for the algorithm. So it depends on which set edges we put together to call it as a matching. Accordingly, the maximal matching could have 3 edges or 4 edges, So the number of edges in the maximal matching that is not always the same across all the maximal matchings. It depends on which combinations of edges we pick. So now this is a graph of 8 vertices. So we can have only at most 4 edges in a maximal matching because again there cannot be a common end vertex for any 2 edges. So in a graph of 8 vertices, you could have only 4 edges so that all the vertices are matched to somebody else. So each vertex is matched to some other vertex. So in that case, we can call the maximal matching as maximum matching because every vertex is matched to something else. Okay. Alright, so among these 4 maximal matchings of edges, the last 2 can also be called as maximum matching. We should also realize that we can have 100% matching of the nodes only if the graph has an even number of vertices. So in a maximum matching is possible with 100% matching only if the graph has even number of vertices. If the graph has odd number of vertices, then we can have only v over 2 minus 1, where v is the number of vertices, v over 2 minus 1 vertices or node pairs matched. Okay, so in a graph of v vertices where v is even, v over 2 node pairs can be matched at most for a maximum matching. Whereas for a graph of odd number of vertices, then only v over 2 minus 1 vertices node pairs could be matched. Okay, so for example, in a graph of let me see. So this is should have a graph of 7. Okay, this is a graph of 7 vertices. So whatever we try, we could match only 6 vertices. Okay, which are 3 node pairs. Okay, so Now what we are going to focus is called the maximal node matching. So as we just saw, a maximal matching need not be a maximum matching. So what we are going to look at is an algorithm that will try to maximize the number of nodes that could be matched. And such a matching we are going to call it as a maximal node matching. Okay. So for example, for this graph, we could come up with a matching like this, and we can call it as a maximal node matching, and that's also maximum matching because every vertex is matched to something else. Whereas for this graph over here, this is what we could come up with as a maximal node matching. And you can see here this is a graph of 8 vertices, but only 6 vertices are matched. So the percentage of matching is 6 over 8, which is 75%. So this is not a maximum matching because every vertex is not matched to something else. But depending on the edges in this graph, this is what we could come up with as a maximal node matching. We try to maximize it, maximize the number of nodes matched, but this is the best we could come up with. Okay. Now again, there could be multiple maximal matchings. So for the same graph over here, 1, 2, 6, 7 is a maximal matching, but it's not a maximal node matching because we could come up with a matching that has 3 edges instead of 2 edges. And that's the maximal node matching because we cannot come up with a matching of 4 edges and call it as a maximal matching because it will violate the property of matching. So now what we are going to look at is an algorithm to determine maximal node matching. Now what is an application of this? This is a lot of applications. For example, given a network of people in a social network or in a company who can work with each other, we want to maximize the number of 2-member teams. So we want to form pairs of people who can work collaboratively. And so the edges capture who can work with whom. So given a network of users indicating who can work with whom, we want to come up with the maximal node matching of the users such that the number of users who are matched is maximized. Okay, so in order to go through this algorithm, we need to understand this notion of what is called the coverage weight of an edge. The coverage weight of an edge simply captures the number of adjacent edges to that edge. So for example, for this edge 1, 5, the number of edges adjacent to it. So what I mean by adjacent edges, the adjacent edges have one of the end vertices also as an end vertex. So for example, for this edge 1, 5, the adjacent edges are 1, 2, 1, 6 and 5, 6 because they have either 1 or 5 as also their end vertex. Now instead of manually counting like this, we can have a simple formula to compute the coverage weight of an edge uv, and it is the degree of u plus the degree of v minus 2. So for example, the coverage weight of this edge 1, 5 is the degree of 1, which is 3, plus the degree of 5, which is 2, minus 2. So 3 plus 5 minus 2, which is 3. Now for this edge, say 3, 7, its coverage weight is going to be degree of 3, which is 2, degree of 7, which is 4, minus 2. So 2 plus 4 minus 2, which is 4, is the coverage weight of this edge 3, 7. So the criteria or the idea behind the algorithm is going to be like go through an iterative fashion. In each iteration, we're going to include one edge to be part of the matching, maximal node matching that you're going to find. And after some iterations, you would have found the maximal node matching. Now, what edges to be included in this set of edges for a maximal node matching? So, what's the criteria for choosing the edges? Now, given that we know what the coverage weight of an edge means, the question is, should we choose edges with a larger coverage weight to be part of a maximal node matching or a lower coverage weight to be part of a maximal node matching? Now consider this particular choice. So for this graph over here, these are the coverage weights of the edges. So the largest coverage weight is for the edge 6, 7. Now if we were to choose the 6, 7 to be part of maximal node matching, what will happen is all these adjacent edges of 6, 7 are automatically getting ruled out to be part of the maximal node matching, because remember the definition of matching, no two edges can have a common end vertex. So if 6, 7 gets picked up for a maximal node matching, we have to exclude these edges 6, 2, 6, 1, 6, 5 or 7, 3, 7, 4, 7, 8 from being considered to be part of a maximal node matching. Then what happens, look at this graph, if these 6 edges cannot be picked up, we have only 3 more edges left over there, and we are kind of diminishing or reducing the chances of finding a maximal node matching because only few edges are going to be out there as candidates. So what we want is to maximize the number of candidates available as edges to be chosen for maximal node matching. That means when we include an edge to be part of maximal node matching, we want to reduce the number of adjacent edges that get discarded from being considered for maximal node matching. So that leads to the other extreme, that of picking the edges with the lower coverage weight. So when we pick an edge with a lower coverage weight, we are only discarding fewer edges to be part of the maximal node matching. So this is a greedy strategy that we are going to employ for this algorithm. Okay, so what we are going to do is in each iteration we are going to pick the edge with the lowest coverage weight to be part of a matching, so that very few edges get discarded from being considered for a matching, and the other we are maximizing the edges that are still available from being considered for maximal node matching. So that's the edge selection criteria. Okay, so given this graph, we have here the coverage weights of the edges, and now we pick the edge with the lowest coverage weight, which is 3, and there are a lot of edges with the lower coverage weight of 3. So which edge we should pick up? Now there's no particular rule, we can break the tie in any order we want. So let us say I pick the edge to 3. You could pick some other edge with coverage weight as 3 also and proceed. I just proceed to pick this edge to 3 to be part of my maximal node matching. So when I pick this edge to 3, it's 3 adjacent edges which are 2, 1, 2, 5, 12, so 2, 6 and 3, 7 get ruled out or get discarded. So I'm going to remove those 3 adjacent edges as well as this edge to 3 from this graph. So this is my modified graph. So I'm going to recompute the coverage weights of the edges in this modified graph and continue the next iteration. So for the next iteration, again I'll choose the edge with the smallest coverage weight, which is 2. There are several edges with a coverage weight of 2. So I break the tie arbitrarily. I pick the edge 1, 5. So because of that, edges 1, 6 and 5, 6 get ruled out from being considered. So they're removed from the graph. So these are the remaining edges. So if I find the coverage weights of these edges, it comes out to be 2 for each of them. So again, I can pick one of them arbitrarily. So let us say I pick 4, 7. So once I pick 4, 7, the other 2 edges get discarded from being considered. So the kind of we have a nice graph in which each vertex is on its own. So we have to continue the iterations until we are led to this situation like this. So this is the maximal node matching for this graph of 8 vertices, 1, 5, 2, 3, 4, 7. So again, as you notice here, we try to maximize the number of nodes that are matched, but we cannot find a maximum matching, in the sense that we cannot find a matching where every vertex is matched with somebody else. So what we have found is a maximal node matching with only like 6 out of 8 vertices being matched. So that's a 75% matching. Okay. So now what we'll go ahead, okay, let us do one more example. So we're again given a graph here with 7 vertices. So this is a graph with odd number of vertices. So definitely it's not possible to find 100% matching. So we can find only like 7 over 2 minus 1. So 3 node pairs at most could be matched for a maximal node matching. I could also give you some weights for the vertices. So this could indicate some characteristic of the nodes. For example, the height or weight or whatever age of the users of the nodes, or say the fraction of the time they spend on gardening or something like that per day. So when you have to find the maximal node matching, we should not consider the node weights. I may give you, but you shouldn't consider to as part of the algorithm that we just went through for maximal node matching. We'll see after going through these iterations when we should use this node weights. Okay. So let us continue with what we like, similar to the previous example. So we'll find the coverage weights of the edges based on the node degree. So the coverage weight of say 2, 3 is the degree of 2 plus the degree of 3 minus 2. So degree of 2 is 2 plus degree of 3 is 4 minus 2. So 2 plus 4 minus 2 is 4. That's the coverage weight of edge 2, 3. Similarly, find the coverage weights of all edges out there, and the minimum among them is 3. So remove the edge 1, 3 or include the edge 1, 3 in the maximal node matching and remove its 3 adjacent edges, which are 3, 2, 3, 4 and 3, 6. So this is the modified graph. Again, find the coverage weights of the edges. 3 is the smallest coverage weight and the corresponding edges to 4. So remove it and include it in the set of maximal node matching and remove its 3 adjacent edges. So we are left with this as the set of edges with the coverage weight for each of them being 2. So we can pick one of them arbitrarily. Let us say I pick 5, 6. So once I pick 5, 6, the other 2 edges are discarded and the graph vertices get isolated. So we have found these 3 vertices, these 3 edges to be part of a maximal node matching. So the percentage of nodes that are matched are 6 over 7, which is 86%. So now what we are going to do is how similar or quantify how similar are the end vertices of the edges that we picked, okay, with respect to the node weights given. So these are the edges, right? 1, 3, 2, 4 and 5, 6. So what we are going to evaluate is how similar are the end vertices of the edges that we pick. So that's where the assortativity index comes. Okay. So based on just these 3 edges that are part of this maximal node matching, we're going to compute the assortative index. Okay, so previously we were using xy as the variables notations. Here we'll use uv. Okay. Alright, so again we'll follow the convention of writing down those edges in this fashion. So the first node ID will be smaller than the second node ID. So u is always going to be less than v for any edge that's being written down for the calculations. So you have 1, 3, then 2, 4 and 5, 6. So we'll call the set u as the first set of end vertices, and set v as the second set of end vertices of these edges. So we are going to do the assortativity calculations based on these node weights now. Now you should realize that we did not consider the node weights as part of any edge selection criteria when we went through this algorithm, when we computed the coverage weight and so on. So for the maximal node matching, we are not going to consider the node weights as part of edge selection criteria. We are going to use the node weights only for computing the assortative index of the set of edges that are chosen for maximal node matching. So these are the node weights, and you know the assortative index is nothing but the Pearson's correlation coefficient of the two set of vertices u and v. So here u and v are these values. So the way we are going to do that is compute the average of u and average of v. So average of 0.5, 0.7, 0.1 is going to be 0.43. Average of 0.9, 0.3, 0.8 is 0.67. Now you find u minus average of u. So the individual values minus 0.43. So that is 0.5 minus 0.43, 0.07, 0.7 minus 0.43, 0.27, 0.1 minus 0.43 is negative 0.33. Similarly, v minus average of v, 0.9 minus 0.67 is 0.23, 0.3 minus 0.67 is negative 0.37, 0.8 minus 0.67 is 0.13. Now square these differences and add those squares values. Okay, so this is the sum of the squares of the differences. Similarly, square these differences for the v and find sum of the squares of the differences. You also compute the product of the differences and compute their sum. So the formula for the assortative index is the sum of the product of the differences divided by the square root of the sum of the squares for the u values times the square root of the sum of the squares of the v values. So this is the numerator, the sum of the product of the differences divided by square root of the sum of square of the u values is 0.1867, for the v values is 0.2067, and that comes out to be negative 0.64. So this is kind of very much a disortative network in the sense, not disortative network, disortative matching of edges that are part of the maximal node matching. So you can realize that when you look at the weights for the end vertices for these three edges, it is 0.5, 0.9, 0.7, 0.3, 0.1, 0.8. So the edges are not kind of close or similar to each other. They have appreciable difference in their end weight, the node weight values. So again, you could consider all the node weights to be in a scale of 0 to 1, but still any scale could be used here for the calculations. So the assortative index in this case is a measure of how similar are the edges that are chosen for a maximal node matching. Okay. So let's stop with this.